Hello everyone, welcome to video number 5, part 1 of the lectures on SWATCUP. In this video I'm going to show you how to calibrate a SWAT model from beginning to the end. There will be many parts to this video which will give you a complete picture of calibration issues. For this video I selected a sub-watershed of Danube River Basin which was part of our European project. I will be using SWATCUP Premium for this video, and those of you that don't have the Premium version, there's nothing to worry about because everything will be the same, except when I talk about single behavioral objective function, multi-objective function, and multi-objective behavioral function. The old SWATCUP version that you have only contains single objective function. So as far as the interface is concerned, everything is exactly the same. So let's jump right into it. The first thing you have to do is to make sure your model is correct. Calibrating a wrong model or an inadequate model is nothing but a headache. And even if you by chance get a good result, it will not be meaningful. So in step 1.1, plot and check if the climate and discharge data make sense. There are always a few different databases to choose from. Make sure that you're using the best ones. Please see the paper below for a discussion on this point. In step 1.2, use the maps option in SWATCUP to get a sense of the watershed you're calibrating. By using the map option, you can check to see if the rivers were simulated correctly in ArcSWAT. Also, you can get an idea about the location of the measured outlets as positioned by ArcSWAT. See where they are with respect to dams and reservoirs. SWAT cannot give you correct simulation of an outlet downstream of a dam unless it is provided with dam discharge. So check if the outlets are correctly located on the right river. Often outlets are not positioned correctly because their coordinates are not very accurate. Using the map, you can also check if you are in a mountainous region where snow melt is an important component. In that case, you must add elevation band to your model, as discussed in a previous video. Then you have to fit T-lapse and P-lapse parameters. And after that, you need to calibrate the snow parameters. Video 4 was all about calibrating in a mountainous watershed. These you have to do first before starting the calibration process. Also check if the region is agricultural, urban, or forested. This should give you ideas about processes and parameterization of the calibration model. In step 1.3, you can exercise the principle of correct neglect. Here you can choose what processes you should include in your calibration model and what processes you can correctly ignore. You can read more about this principle in the paper shown below here. So make sure you account for important processes. Some of these processes include agricultural management, such as planting, rotation, irrigation, fertilization, etc. They include point sources, like water treatment plants, springs, if you are in a mountainous region, etc. These could be inputs or outputs to the system. Also, you need to check if there are water transfer from your watershed, if there are dams and reservoirs, if there are potholes, or if there are other things happening in the watershed. There are some processes that SWAT can handle, and there are some processes like wetland processes, glacier melt, etc., that SWAT cannot handle. So make sure that you include things that SWAT provides option for them and can actually handle and include it into the modeling process. In calibration step 1.4, check the river connectivity. If your burning rivers, for example, are disconnected, such as this here, you can get flow going in the wrong direction. Or if the river doesn't extend to the edge of the watershed, for the rivers that should flow out of the system, like to a lake, for example, then you may get rivers going the wrong direction and coming into the system. A good way to check this is to plot the flow path or the flow direction map. I will show you later how to generate this map. This tells you if flow direction is correct or not. See the paper below also for more discussion on this. Next, in step 1.5, check if the measured outlets are on the right river. Very often, outlets are put on the wrong river because their coordinates are not very accurate. Make sure they are on the right river. This outlet was initially put on a tributary of the Danube. So its given location was this, SWAT will put it on the nearest river, which is this one. It's a tributary of the Danube. Whereas it should have really been on the Danube itself. So what happens is, if we simulate it on the tributary, this is what we get. That's the measured data, and here is the SWAT simulated data. But if you put it on the right river, on the Danube, then you can get the graph shown down below here. Now this can be calibrated, but this situation cannot be calibrated, and it just gives you a huge headache. So, okay, in calibration step 2, or perhaps I should have called it pre-calibration steps, you need to prepare the observation data. As you know, SWAT outputs a lot of different variables in a lot of different files, and theoretically you could use any variable or variables in these files to calibrate your model. So for example, flow, sediment, nitrate, phosphate, things that we usually use, they reside in the reach file. In the HRU file, you have potential actual evapotranspiration. In the sub file, you have sort of the same things, but at the sub-basin level. In the sediment file, you have sediment in and sediment out. In the reservoir file, you have flow in, flow out into the reservoir. In the soil moisture file, you have soil moisture for every layer of the soil. And then crop yield resides in the management file, and so on. For each of the output files, say output.reach, we have a program that extracts data from that file. And you need to create for that an observation file. For crop yield, you should always use the output from the management file. And in here we have two different files, one for crops that you can either harvest only and harvest kill, or you can only harvest and kill. So the first one would be like grass. You can harvest a few times during the year, and then at the end you may want to harvest and kill. And then for crops such as wheat, that you only do harvest and kill. So there are two different files to handle these different types of crops. To summarize, let's take, for example, output reach. For this output file, we have a program called extract reach exe file, and the star stands for the algorithm, either SUFI2, SPE, PSO, and so on. This program needs these inputs. Next to the output.reach, you need to define what you're going to extract and when, from what subbasins and at what time. And then you have an observation reach file where your observation resides. And then you have a variable file reach where the variable names are there. And then you get the desired output from this program. So let me just show you where these files are. You should sometimes leave the interface and go to your SWATCUP project folder and see what else you have in there. There is a lot of information there that really they don't fit in the interface. But as you get to know the program, you may not even need the interface to run the program. But these files, as I mentioned, in spe.in, we have the observed reach file is here. In this file, we have 16 observation file, and this is the format of it. I have covered this before, so I don't want to spend too much time here, but this is a sequential sort of date from beginning to the end of the simulation. And here is some information, user-defined information, so that you know what you have. This is, for example, flow out from subbasin number 6, and that's the date, and that's the flow. So we have about 16 different variables here. We have some 11 different flow variables, and then at the end we have about five different nitrogen and nitrate variables here. And then the other file is the variable file reach. Here, as I said, we have the names of the output files here, some 11 flow from different subbasins, and then nitrate, 5 nitrate from different subbasins. And then we have in the main folder, you have the definition file. The definition file is important because it's telling the program what to extract where. So here it's quite self-explanatory, these files. So we have two variables, column 7 and column 18. That's flow, that's nitrate. That's the total number of subbasins in the project. So we have 11 subbasins where we have observed flow, and these are the number of subbasins, and we have 5 nitrate observations from these subbasins. And then that's the beginning and the end of the time, not including warm-up period. Many people make mistake here. This is not including warm-up period. And then that's one. The other thing is that these are sequential, right? I write here they should be in increasing order, right? So don't mix them up from everywhere. So they have to be always in increasing order. And in the same order they appear in the observation file. So these simple files you have to make. The hardest thing is to make this observed reach file. Okay, next in step 2.2, you need to divide the observation data into calibration and validation data periods. And to do this, in general, we need to follow two rules. The first is that calibration data should contain all kinds of climate situation for parameters to be generally usable. That means you should not calibrate only for wet years or dry years or monsoon years and so on. So your calibration data set should contain all kinds of climatic situation. And then the second thing is that the statistics of the calibration period and the validation period should be similar. So the average, for example, the average and the standard deviation of the calibration period should be the same, more or less, the same as the validation period if you want to have a good validation result. So that means, again, do not calibrate for wet years and then try to validate for dry years. So to achieve this, you need to play a little bit with the cutoff point of calibration and validation. So here is an example where I have calibration data, the average and the standard deviation, and the validation data, also the average and the standard deviation, which are more or less similar. Furthermore, your calibration period and your validation period, they don't need to be like, for example, from 1990 to 2000 you calibrate, and then from 2001 to 2008 you validate. Of course, it could be like this, but you're not limited to this. You can have calibration data to go from 1990 to 1995, and then from 2000 to 2005. And your validation data from 96 to 99 and from 2006 to 2008. So that way you have more flexibility to, first of all, make sure that your data period for calibration contains all kinds of data, all kinds of climate situation, and that also the statistics of the calibration and the validation periods are sort of similar. Now, as I said before, the hardest thing in preparing input files of SWATCUP is to make the observed reach file and the observed.txt file for calculation of objective function. To make life easier, I have created a program called Make Observation Files. And this program resides in the utility program. So if you go to the utility program, there are different utility programs that I will explain at the right time. But now we are dealing with Make Observation File. I have already explained Make Elevation Band. We have a video for this. And to make the observation file, it's quite simple. I can probably show you now how you do it. Once you activate this icon here, what you get in your project folder is a folder called Utility Programs. But to make observation file, if I go to Make Observation File, each one of these utility files has a README file where every step is explained. Folder called Data. In this folder, you have your observations. This is a generic format, say flow out from 6. In this file, you have your flow out from 6. This is the sequential from beginning to the end of the simulation, always from beginning to the end of the simulation. This is the date. It's also sequential from beginning to the end of simulation, and this is your discharge. So if you make every one of your output files in this format, then you can run the program, and the program will make you the observation file, the observation HRU file or reach file, and so on and so forth. And every file has the same format from beginning to the end of simulation. And if you have missing data, you simply specify a -99 to indicate the missing data. So here we have a whole bunch of missing data, and then we have data. And the same thing goes for everyone else, and also for nitrate. For nitrate, from beginning to the end of simulation, and then we have all this missing data for these years, and then at the end we have some data that we are going to use for calibration. So if you make all your observation in this format, then all you have to do is to create a definition file, and the definition file says simply the type of simulation, if it's daily or monthly, the data, the variable qualifier, for example, nitrate out, flow out, and so on. And then the missing variable, the missing values, how you indicated the missing values. Here we have -99. And then beginning year and end year. So this is beginning of the simulation, year, month, day, and end of the simulation. If you create this, you run the make observation file, and this will create for you observation files and put it in the output. In the output, you will have the observed text. In the observed text, you will have this is the file you use for objective function calculation. So there are some things that it's user defined and you need to fill. They are indicated by question mark. For example, the type of objective function that you want to use. And this is the multi-objective function value weights. These are the weights that you have to give if you want to use multi-objective. And then this is the minimum value objective function threshold that you need to fill. And the rest of it, it's all prepared for you. And then also prepared is the observed reach file. And the observed reach file, that's a number of observed variables, and we have nitrate, and the 5 nitrate are specified here. So the file is made. Then we also made the SP extract reach definition file. This file just gives you these subbasin numbers, the sequential subbasin numbers, but the rest you need to create. And then you have the variable file reach, which gives you the name of the variables that you are using from that file. So now for the rest of this video, I'm going to show you how you make this flow path, and then we will continue this lecture in the next video. All right, so to build the flow path or flow direction map, what you need to do is you need to go to your ArcSWAT project, and from the shape folder in the ArcSWAT project, you need to get the river1 shape file. And when you get this, next you go to here to the properties, and then you choose the symbology, okay, this here, and then you go to categories or go to quantile, and from the quantile you choose the graduated color, and for the value you choose width 2. This is the width of the river. And then from here you get initially 5 divisions where you can increase or decrease, or and then from this what you do is for each division you choose I usually choose blue color, and for the first one I choose a width of 0.5. okay, for the next one you choose a width, choose the same color and a width of 1, okay, and for the next one you choose again the same color and a width of maybe 1.5, and then the next one again the same color and a width of perhaps 2, and then the last one same color again and a width of maybe 3, and okay, and this gives you your flow path, as simple as that. Now with this map you can identify if your river is going to the right direction, because as river goes from upstream to downstream in ArcSWAT, its width will increase. Therefore this is showing you the direction of the flow. So here this is a map of the Black Sea, and here we have the Black Sea itself. So we know that most of these rivers have to come into the Black Sea. So if you have a river which is going the other way around, it's getting thicker in the opposite direction, then you know that your flow is not correct and the river direction is not correct. So this is one way of checking whether you have digitized your map correctly and the rivers are correct and your flow is going in the right direction. So if it is going in the wrong direction, of course you can imagine what kind of a problem you're going to have when you try to calibrate that. So this would be the end of this 5-part 1 video. I will make the next one. So if you want to be notified about the next video, please subscribe to our channel. Thank you.